form of asteroida, black holes, supermassive black holes, feedings of supermassive black holes. So it's one of the most interesting topic which catches the public psyche, and it's a lore of our popular scientific culture. Also, people like to know about black holes. So we have with us Dr. Niraj Gupta, and I will just introduce the speaker before we actually go into the topic. And this program is a joint venture between Regional Science Center and Planetarium Calicut and Public Outreach and Education Committee of Astronomical Society of India. So this is done monthly, and this is the 10th episode in its number. So, Dr. Niraj Gupta, he works as an associate professor in Inter-University Center of Astronomy and Astrophysics, or IUCAA, IUCA. His research focuses on interstellar medium of galaxies, and he is involved in various observational projects with current and upcoming radio telescopes to trace the evolution of cold atomic and molecular gas content of galaxies using absorption line. He is a co-principal investigator of Meerkat Absorption Line Survey, MALS, a large survey of H1 21 centimeter and OH hydroxyl 18 centimeter lines at the Square Kilometer Array, SKA, precursor of Meerkat radio telescope in South Africa. He is interested in observational techniques relevant to large blind search of absorptions line at radio wavelengths, and he leads the design and development of automated radio telescope image pipeline responsible for processing vast amount of MALS data. He is born in Delhi, and after his master's from Department of Physics and Astrophysics, Delhi University in 2001, he joined NCRA, National Center of Radio Astrophysics, and obtained his PhD from the Tata Institute of Fundamental Research in 2007. Before joining IUCAA in 2013, he worked as a postdoctoral fellow at Australian Telescope National Facility in Sydney, Australia from 2007 to 2010, and Netherlands Institute of Radio Astronomy, Dwingelo, Netherlands in 2010 to 2013. At ATNF, Australian Telescope National Center Facility, he designed an antenna configuration for Australian Square Kilometer Array Pathfinder, ASKAP. So we have a very learned and proficient speaker on this particular topic. He's an experimental scientist, and he will be throwing a lot of light and not like unlike our previous Astro Adda, this time we thought that it will be in a more informal mode, in that way that I will be asking the speaker as if I want to know certain aspects, and also I invite all of you to join me in that particular way, and maybe wherever you feel that you can also interrupt and you can ask, so that it will be more engaging rather than passively the speaker comes and speaks and then we listen, and at the end we have a question answer session. So that is a bit deviation from our last time. So, Dr. Niraj Gupta, welcome. And now I think we can formally start. So you know that black holes are popular. Anybody, wherever you go for a talk or wherever you go for interaction among college students or school students, the questions which people wants to like to ask is about black holes. So what are black holes? Can you start your talk with providing some answers, and why they are so significant? They occupy such a place of such a significance in astrophysics and popular culture.
So as we talk today, we are at a juncture where astronomers are talking about imaging black holes, and later in the discussion today, we will also try to understand that why they acquire such a prominent place in astrophysics. In fact, without understanding the effects of black holes, we cannot really understand the evolution of galaxies in the universe. That's one of the themes that we will try to explore later today. But before going into that, just to understand that why black holes have acquired such a prominent place in all our discussions, it is, I think, interesting to just go back maybe about 100 years in time and try to identify some of the major milestones in our understanding of black holes, how it has evolved. So if we go back in time, approximately 100 years ago, then at that time, physicists understood that, of course, under the influence of gravity, objects can collapse. But it was not really appreciated by that time that to what extent they can collapse. That is, if you take a body of, let's say, few solar masses, and if there is nothing to support it, for example, when we look at our sun, then sun has certain mass, then it's actually under the influence of that gravity, it can collapse. But the fact that there is nuclear fission going on, the gas inside it is hot. Because of the thermal pressure, this gravity is balanced and sun does not collapse. But then there can be situations where this pressure is no longer there to support and then at that time, this object can continue to collapse. And if that happens, whether it can lead to formation of black hole or not, it was not really understood. So theoretically, it was initially proposed that yes, such a thing can happen. And of course, we know that Chandrasekhar did a lot of work in this area, and he proposed currently known as Chandrasekhar mass limit. And then, but even at that time, it was not really well accepted idea around in the community. It was only when we came to around 40s and 50s, like about 2 decades after that, that the theoretical understanding was advanced enough to understand that, okay, if the object is massive enough, then it can continue to collapse under the influence of gravity. And it can lead to formation of exotic objects like neutron star. And around the same time, the technology was also advanced enough, and people started discovering what is known as now pulsars, which are like nothing but rotating neutron stars, right? So this was the time around which it became apparent that these massive collapsed objects can form, and then they can actually even lead to the formation of black holes, right? And then further, when even better telescopes became available, people started discovering objects in the sky which were producing copious amount of energy, right? And that energy was at times so large that it will outshine even the galaxy, right? It's coming from such a tiny region, but it produces, then the amount of energy is so much that it outshines the entire galaxy. And it was not possible to explain that how such a large amount of energy is produced by any known physical process at that time.
So are these that active galactic nuclei you're speaking about?
Yes, absolutely. And I think let's before going into active galactic nuclei, let us just try to understand one more thing, and then I will quickly come to the point of active galactic nuclei. So when we are talking about black holes, we are talking about objects which have collapsed to such high densities that and they have such a strong gravity that we can only understand their or realize their presence through their gravitational effect, right? Even light cannot escape if it goes beyond what is called as event horizon of a black hole. So currently, it is understood that almost every galaxy that we have in the universe actually has a black hole at its center, a supermassive black hole. And when I say supermassive, I'm talking about black holes which have mass million times the mass of sun or more than that. So what we are seeing here is a cartoon which is showing, you can see the label here, Sagittarius A star. So this corresponds to the galactic center, that's the center of our Milky Way. And what these bright blobs are here, they are different stars close to the center of our galaxy, right? So what astronomers actually have been able to do, and this is an experiment which is going on for last 30, 40 years, that they are actually observing these stars, the motion of these stars around this dark spot here. Like it's a black hole, we cannot see it, And you can see that there are these different panels which show different snapshots of these stars at different time. So you can see that they are following certain trajectory, and following this trajectory, we can not only infer that there is a black hole at the center. In fact, the mass of this black hole is few times 10 to the power 6, that is approximately million times the mass of our sun. We can also try to understand that whether this black hole is spinning or not, and what are its other properties, right? So by doing such very careful experiments, one can, even though we cannot see it directly, we can actually infer its presence, and we can also determine its properties. Now, coming back to the question of AGN, or the active galactic nuclei. So what happens that when we have this supermassive black hole sitting at the center of galaxy, it is not in vacuum, right? Because galaxy has a lot of gas, lot of stars, and in fact, if you go towards the center of our galaxy, we are talking about an environment which is much more dense in terms of gas as well as the stellar density. So there are much more stars there in the central region of the galaxy. So what happens that because of the gravity of the black hole, then the matter which is around it, it begins to gets pulled in. And now this gas also has what is called the angular momentum. So instead of just falling in radially, it will actually spiral down in, and it will form, as we see in this cartoon here, what we call as an accretion disk, right? And in this accretion disk, this matter will also come across, encounter a lot of friction, so it will be heated up. So then it starts actually emitting radiation, which is not bound to just the optical light, which is something we can see with our eye. It actually radiates across the entire electromagnetic spectrum, which means that we can observe these AGN, or the active galactic nuclei, at wavelengths starting from gamma ray, X-rays to visible, and then even the millimeter and the radio waves also. Right. So this is such a energetic phenomena.
So what I mean is that first of all, there is one question. As you're saying that this accretion is occurring, so yes, the jets are formed on either side. So why should a jet be formed? Can you people may like to know, or
yes,
why should the jet form in that?
Yes. So there are two interesting aspects. First is the mechanics of it, right? The mechanics of it is such that as the matter is coming in, there is no other way it can escape, right? So there are certain situations where it can actually start getting ejected in the perpendicular direction, the direction of the least resistance, right? And these jets are actually made of plasma, that is the charged particles, and they are collimated by magnetic fields. And they can actually travel outwards to the distances of kiloparsecs to the megaparsecs. And we'll come back to this point that how it can actually allow AGN to actually impart this effect to such large physical scales, right? Because when we are looking at this cartoon here, accretion disk and all, we are talking about scales which are much smaller than parsec. But then these jets, when we are talking about, they can actually go out to distances of the order of even megaparsec. So that's the first point. Another thing is that these jets are not always formed; they are present, right? It's only in one out of 10 AGN that these jets are formed. But it is not easy to say whether it is that 1 out of 10 AGN will form a jet, or that all AGN in 10% of their lifetime will be forming a jet like that, right? So that's the kind of enigma or the dilemma that we have to resolve through observations. But this shows that these jets can actually allow AGN to impart its impact over a much larger region.
And these can be observed in all the wavelengths.
Yes, yeah. Actually, let's move forward. So what we are seeing here is the entire electromagnetic spectrum on the x-axis here, right? And the first image that I showed here, it was at optical wavelength. It was made using VLT, a very large telescope. It's based in Chile. It's run by ESO, called European Southern Observatory. And the instrument that was used is called Gravity. It's specially designed to observe these kind of stars. And I will talk about some of this technique, which is based on interferometry later in my talk. But coming back to this one, so this is the wavelength regime that we were looking at in that panel. And we can observe AGN at radio window here, for example. We can also look at certain aspects of AGN in ultraviolet or X-rays, where we have to employ these space telescopes like Hubble Space Telescope or Chandra, and in future, or now already actually James Webb Space Telescope. So why do we want to look at AGN or even want to do astronomy at different wavelengths? I think just to quickly appreciate this, let's look at this uh, view graph here, which is nothing but showing our own Milky Way at different wavelengths. In top panel, what we are seeing is the image of our Milky Way at 408 megahertz. This is very low frequencies that we are looking at, right? It's in terms of wavelength, it is very close to 1 meter in wavelength, right? That much that we're talking about. And then as we are coming down in these panels, we are going to higher energies. Like we are looking at in an optical here, then we are looking at an X-ray. So what we are seeing here that in the topmost panels, we are looking at gas or the charged particles in the galaxy, which are radiating through a process called synchrotron. This is basically charged particles going around the magnetic field, and they are emitting radiation because of that. In the visible image, we are looking at actually younger stars, but we are also seeing that radiation is blocked by a lot of dust here. These are the dark patches corresponding to it, because dust particles which are present in the galaxy have size which is of the same order of the optical wavelength, so it is getting blocked. But when we are looking at these longer wavelengths, they are able to go around these dust particles, so they are not getting blocked, right? And when we are looking at, for example, this infrared image, then we will be looking at older stars in the galaxy. This is so just the same object is when we look at different wavelengths, it's showing us different physical process that is going in there and showing us a different component of it. So similarly, it happens for AGN that when we look at a different wavelengths, we are probably probing different region of this accretion disk, or when we look at it, for example, at radio wavelengths, we come across these spectacular features. So let's spend a little bit of time on these two images. On left hand side, let us first look at what we are seeing here is an optical image in the background, and these colors that we are seeing here, these jets kind of thing, they are seen in radio. So in optical image, when we are looking at, we are seeing this disk of the galaxy, right? And we are also seeing the halo of galaxy, which has these older stars. And then in the disk of the galaxy, there is a lot of dust, which is forming these dark patches, right? And there is a supermassive black hole at the center, and it is active. And we know its presence also through these jets which are being formed here. You can see that they are so much larger than the size of the galaxy. And these jets are actually now seen only at radio wavelength. So if I am looking at only the optical image of this galaxy, I will not be able to observe this phenomenon. On the right hand side is another example, which again shows that like these highly collimated jets travel so far out in the intercluster medium, deposits their energies, and they form these large structures of plasma, which we call as radiolobes in this case, right? And there's another manifestation of this exactly same thing. On left hand side, again, now what we are seeing is that, so previously we were looking at radio overlaid on optical. This is now a different object. In this case, we are looking at radio, which is in red. So we can see these jets, radio jets, and they are very distorted because they're interacting with the medium, so they cannot always travel very freely. It depends on how dense and clumpy the medium around is and how powerful the jet is. And then in blue, we are seeing X-ray. So X-rays are probing really hot gas in which this entire medium is embedded. And we can see that there is a cavity wherever the radio jet is, and this is because the radio jet are depositing large amount of energy in the medium here. So this is another manifestation of how these small tiny object which is sitting here, tiny but not insignificant because it's very massive. We are talking about black holes which are of like billion solar masses, but it can, through this physical energetic process, it can actually impact such large environment around it. And we are talking about here a process which is so efficient that the 40% of the matter that is actually going into the black hole gets converted into energy. And if we want to compare it to a stereotypical our nuclear process, there less than 1% of energy is actually of the matter is converted into energy. So it's such a efficient process in converting matter to energy.
I'll just interrupt here a bit.
Yes.
since we are speaking about 40% and the percentage of matter which falls and it converts into energy. So somewhere I have read that actually the black hole's area goes on increasing. So is there any way of relating, means how much matter is falling and the area?
Yeah, so if we talk about the formation of black holes itself, like so to start with, there would be stellar mass type black holes, right? Because depending on if the mass of a star exceeds a certain number, and then if the fusion stops, then after it can collapse and form a black hole. But then after that, then it can start continue to accrete matter, and depending on the kind of environment it is, then it can also merge with other black holes, for example, right? And through this process, then it can continue to grow and it can actually grow to black holes of sizes of, like, for example, billion solar masses, as we see in this case.
Yeah.
So how does we? So we are looking at. I think through these slides, I think it's obvious for us to appreciate that black holes, in the form of active galactic nuclei, can actually transport energy to a very large region around it. And this becomes very crucial for us to not just really understand AGN as these, not just as beautiful objects, but also to understand the galaxies. So let us just look at this plot actually, and we will spend a little bit of time on this because I think if you really want to understand the big picture, sometimes it becomes important to understand and look at a lot of data, right? And I think, and a lot of us, and almost all of us, have become a bit of statistician in last 2 years because of COVID, right? Because every day we are checking like how many cases, whether it's going up or going down. So I think most of us are now familiar with this kind of plots. So what we are seeing here on x-axis, we are seeing what we are plotting here is the total mass, right? And I will explain total mass of in a bit. And on y-axis, we are plotting number density in a way, right? So what is this blue curve here that we are looking at? Blue curve is actually the observed stellar mass of galaxies that we observe, right? That's what we are looking at. So we see that like there are galaxies of this certain mass, and then we come to very high mass objects, and they have a certain difference. That's it. Or what is this dashed line here? Dashed line is corresponding to the total mass that is there. Total mass is not just the stellar mass, but also the dark matter which is there and everything else that is there in the galaxy. So what we can infer from this directly is that at this point, galaxies are actually very efficient in converting gas that is present into stars, right? Whereas, like if you go to very low mass galaxies, this gap is much more, right? So efficiency is less, and even at this other end, the efficiency is much less. So this is purely coming from the observation. And when we apply all the physics that is known to understand the formation of galaxies and how efficiently they can convert gas into stars, the astronomers are unable to reproduce this. But what they find is that something which is like similar to this dash curve, right? So what they have to do is to find some means through which they can actually quench the stars from conversion of gas into stars at very low mass end of the galaxies. And at very low mass end, it is not very difficult to do because a smaller amount of energy is required, so we can use things like a few supernova are often enough to heat up the gas, and then it cannot form stars. Why is that? That's and something. Another interesting point here is that when we take a cloud of gas, right? It will, when we say that it will form star. What does it mean by it will form star? It will form star means that it will continue to collapse under gravity, and at some point the density will be so large that it can actually the fusion can start, right? And then that's when we say that okay, star is formed. That's what has to happen. But for a cloud to continue to collapse, it has to have a certain low temperature, right? Because if it is temperature is high, then the pressure will be high, then it cannot collapse under the gravity, right? So the gas has to be really cold, right? But how cold it has to be 10 to 20 Kelvin, for example. Only gas when it cooled to such temperatures that it can collapse to such high densities that it can actually form stars. So at this end, Q supernova can actually heat up the gas and even expel it from the galaxy. That star formation can stop, right? But when we come to this high mass end of the galaxies, supernova from a few stars is just not enough to stop the process. We need something much more energetic, and nothing more energetic than AGN feedback is possible here. So that's what I meant when we were talking initially in our discussion that like it's not just that we need to understand black holes and AGN, but we need AGN as a whole to also understand how galaxies are forming and actually evolving as the throughout the history of the universe. So that's why AGN feedback and AGN occupy actually such an important place in not just the popular culture and in our trying to understanding of cosmology, but also just the basic astrophysics as well.
Yeah. So this is a very impact-making picture, which lot of in media it was covered well, and people are actually trying to understand what this picture conveys. So I think you have to describe this picture because Event Horizon Telescope and this picture has become very famous. So please, I think you.
Yes. So there are two very exciting things when we look at this picture itself. One is that what is it that we are seeing here, and the second is that how is it that we make it, right? So let's tackle these or appreciate this image in these two parts. So first is that if I go back here, let's look at this, right? So this is black hole and this is the accretion disk here, right? So if I remove this accretion disk, so it is this accretion disk and this jet actually, right? Which is what is emitting radiation. If I remove these two, there is just black hole and there is no way I can see it. I can only see it through these stars like that, right? And this kind of experiment I can carry out only for Milky Way because it's close enough. And at present, there are no other instruments for which we can carry out an experiment like this for external galaxies, right? So when we talk about external galaxies, the only way we see them through this radiation which is coming out of it. So now let us imagine that there is a black hole which has this accretion disk. So this accretion disk will be illuminating, right? So we are talking about now a very compact region like subparsec region that we are talking about. So we have to make an image. If we want to make an image of this, will be of the order of we need a resolution of like tens of micro-arcsecond, right? And if you look at moon is like we are talking about a degree kind of a thing, right? So that's the kind of fine resolution that we need in the sky. But and if you make it an image, this is how it will look like. It should look like that. That's what will be our expectation. But that's not what happens, right? So what we end up seeing actually is something like this, right? So in this case, what is happening? The target that was imaged has an accretion disk, something like this, right? But we instead are seeing a donut kind of a thing, which is face on, right? So surely one thing which is sure that there is a black hole at the center, and that's something, and we don't expect to see anything corresponding to that. And then there will be an event horizon around it, right? That's corresponding to a Schwarzschild radius. So anything that goes inside it, even light cannot escape. So there should be a dark spot again there, right? But what we are seeing, the hole that we are seeing here is actually not corresponding to even that event horizon. It is actually few times, perhaps 2 to 3 times larger than the event horizon itself. And it corresponds to what is called the photon sphere, right? What means that like a photon that comes here actually, and it's an unstable orbit here, it can actually fall into it and it can actually escape it from here. So now visualize the following scenario that there is an accretion disk here. It's face on, it's edge on, right? in this case. So the photon which is coming from the back side here can actually come around it actually, right? This is because there is such a heavy mass here that the space-time is warped, that as a result of it, it can come around and form an image here. It's equivalent to that. If I am, for example, sitting at the black hole, I will be able to see the backside of my head. Right? That's the kind of thing happening, right? And that's what will happen. And then similarly from the other downside also, right? So that's what will be formed here. Right? So that's what is happening in this case, that we are seeing actually the backside of the action disk. So now another question is that why this side is brighter than the top side, and what happens that the matter which is actually going around this black hole accretion disk, it is actually moving at relativistic speed, close to the relativistic speed, so a fraction of the speed of light. And when the matter goes at such a velocity, what happens that the phenomena goes by the name of what is called a Doppler boosting. That it is nothing. It's very similar to Doppler effect in sound. What happens that the object actually of certain luminosity is moving towards me. In that case, it's actually will appear brighter. If it's moving away from me, it will appear dimmer, right? So now imagine this. It's going like this. So the part which is going towards moving towards us is actually brightened, and the parts which is going away from us actually are dim. So this entire thing is actually due to the two effects, that there is this space-time which is warped because of the strong gravity here, and the fact that the matter is going around such speeds close to the speed of light. And I think next, let us move to the question that how such an images can actually be formed. And for that, we have to resort to something called radio interferometry, interferometry basically. And just to quickly understand what does this mean, if I want to make an image at any wavelength, for example, at an optical wavelength or radio wavelength, you can visualize a telescope at optical wavelength. It will be, for example, a lens of certain diameter d, and at radio wavelengths, we can think of it like a dish, again of diameter d. Then the resolution or the sharpness of the image that it can form goes by lambda by d. Okay, and lambda here is the wavelength at which I want to observe, and d is the size of the aperture, right? And if we talk about radio wavelengths at 1.4 gigahertz or something, then even if I make a dish at, let's say, 100 meter or 50 meter, which is corresponding to giant meter radio telescope in India, this is among the largest radio telescope in world, then we get a resolution of close to half a degree or something, right? With which we cannot even barely see the details of moon, right? We think that's such a, and this image is actually made at much higher frequency. It is made an image like close to 200 to 400 gigahertz at much higher frequency. But if you want to get this micro arcsecond order resolution, then we need to make a telescope which is of the size of Earth, right? It's not, and of course, the engineering, with no engineering, we can actually make dishes, even steerable dishes, which are larger than 100 meter or so, and that's pretty much the largest steerable dish that we have. So instead, what we do is that we actually do what is called interferometry. And in this case, what is done is that instead of trying to make a very large dish, and of course, it's not possible to make a dish of the size of Earth, we take multiple dishes which are distributed across a much larger distance. And in this case, what we do is that we take a signal from each one of the dishes, and we combine them digitally. And when we combine them, we collect a certain voltages. And what we are doing here is that we are actually sampling the radiation field which is incident on this telescope, and we are actually measuring both amplitude and phase of it. And through this, we are able to synthesize a telescope actually through this technique, which is called as aperture synthesis. We are able to actually synthesize an aperture or the telescope which is of the size corresponding to the region over which the dishes are distributed. Just to give a more reasonable example of it is like look at this GMRT giant meteor radio telescope, which has got 30 dishes, which are spread over 25 kilometers. It's situated close to Pune here, about 90 kilometers from here. And if I take the 45-meter dish of it and observe the sky at 1.4 gigahertz, for example, I will get a resolution of close to half a degree, right? But when I use this interferometry technique, I am able to make images which are of their resolution corresponding to an aperture of 25 kilometers, which corresponds to 2 oxygens only, right? So Event Horizon Telescope team used this technique of aperture synthesis to make this image, and this technique itself actually got Nobel Prize in 1974, right? Because the demonstration of this, the roots of this technique actually go back to even the experiments like Michelson interferometer in 1907, for which actually Michelson also had gotten a Nobel Prize. But Martin Ryle, who actually demonstrated radio wavelengths and made it physical, demonstrated it works, they got a Nobel Prize for this in 1974. So that's the kind of thing that made this image possible.
But then, why did it take so much time? Because aperture synthesis was known for long back. You said in 1974 it got Nobel Prize, but then we got the image after, because this technique was known, but so technology is known. So why it took so much time to?
Yeah, that's a very interesting question because the technique was known, got established, but to convert it into larger telescopes requires resources, and it progresses step by step because, for example, a Green Bank telescope, which is the largest steerable dish, got set up only in, like about 20 years ago from now, and GMRT also got commissioned in the again, like about 25 years ago. So it took time for technology to evolve to a level where one could efficiently carry out an experiment such as this, where telescopes are distributed across the globe. Because it's not just about setting up those telescopes, you have to record those signals at with a certain precision, and that requires very accurate clocks. And then you have to be able to combine them signal, and you end up collecting terabytes of data in very short amount of time. So you have to have technology where you can store them on disks, and then you must have computers or hardware where you can actually multiply these signals and take for example, Fourier transform of these, which is what led to the formation of these images. So the entire software, hardware, and the engineering has to progress to a point where it becomes practically possible. And even for the Event Horizon team, which carried out this experiment, it took them 2 years to actually collect all the data and process it and then make this image. So it's not that even now with all our advancements, it was a easy experiment to carry out, and it required the global community to come together to perform this. And that's the way larger projects and complex projects move. They require all the intellectual and financial power of global community to actually come together and carry out experiments like these. These are really advanced and massive experiments.
Niraj, can I ask you one question? Arvind Paranjpe here.
Hi, Arvind. Yes.
Yeah. See, I mean, I'm also asking about this, that when you transported data from one station to another, I think it was collected from 6 different stations, right?
I think it was more than that. It was a dozen stations, I think, in this case.
Yeah. So then it had to be having some kind of a timestamp also, isn't it, in order for you to collect all the data and make pictures out of it?
Yes.
So that also must have been a technology by itself to time it accurately, that every data has some kind of exact timing so that you can sort of correlate all the data points.
Oh yes, so it requires we cannot use our standard clocks. We have to use maser-based clocks and things which have like very high precision, so that the time stamping is done at nanoseconds or better, so that then we can take it and we can combine it with that accuracy. Because even a small shift will lead to decorrelation in signal, and we will not be able to do anything with it.
Okay. Thank you so much.
And each station had to have that clock in this case, right? Because they couldn't talk to each other in this case because they are spread so far.
Right. How did you synchronize the clocks then? Or I'm sorry, I have also heard that you could use pulsars as a standard clock or something. I'm not sure. I have not studied that. So just wanted to check with you.
So just for synchronization, GPS, for example, based.
GPS will do.
Yeah, do. And then after that, you let the clock take over. And when we talk about pulsars, pulsars are among the most stable clocks known universally. And in fact, some of the pulsars have not changed over decades now. So the idea is to use these pulsars to carry out tests of extreme gravity, basically, like tests related to Einstein's theory of gravity.
Basically. Yeah. Thank you. Thank you very much.
Yeah. So it's a very exciting time actually for astronomy in general, and also for our Indian community, because India is now participating in a lot of international projects, because all the astronomy projects now are of international in nature, because as we saw in case of Event Horizon Telescope also, that now the kind of things that a scientific community wants to do is actually at the level where it requires people to pool in their resources globally and build bigger instruments, because we want to have a sharper view of the universe. We want to be able to detect objects which are much fainter, much further. We really want to do things, look at things which have not been seen before. It's not possible to do what one single country can build on its own. So India is, for example, part of Square Kilometre Array, which is the world's largest telescope that is coming up in Australia and South Africa. And in the context of black holes, LIGO has been in use for last 5-6 years very much. India is part of LIGO, and one of the LIGO stations will be based in India. And in case of LIGOs, we are talking about actually hearing black holes. In this talk, we have focused on looking at black holes or their effect. In case of LIGO, we are hearing black holes, like the impact that they make on the space-time, for example, when two black holes would, or two massive gravitationally collapsed objects would merge. That's more accurate way of saying, right? So at IUCA, we are also preparing for our participation in SKA, and this is one project that is running on WeCat telescope that IUCA is leading. Some of us at IUCA are leading, and this and there's one strong component here based on AGN and black holes here, is that we are using this large survey through this WeCat telescope to actually understand how the cold gas in AGN is evolving as a function of redshift here shown, which is nothing but the age of the universe. And this redshift range is of particular interest because if you look at how the AGN activity as cosmic history is evolving, it actually peaks at around redshift 2 to 3 and then falls off rapidly after that. And same thing happens for the star formation in galaxies also. So it's a very interesting redshift range to look at. And when we're looking at black hole accretion days, they are embedded here in the center of the very dense environment, the galaxy. There is this question that how actually these AGN are fed, and then what kind of impact they can have on the cold gas in the galaxies, right? So this is the basic theme that we are trying to make further progress in understanding through this project. So this is a very good time for people to get involved in AGN physics or even anything to do with upcoming telescopes at an international stage.
One thing I just back, you spoke about this new Event Horizon Telescope. Now, this whether there was any specific means the locations where these telescopes are chosen together for this particular project. What all factors they considered for this particular imaging project? Means,
Yes, so I think the most so therefore they did not build a telescope of their own.
yeah, they
Uh,
have
so,
yeah.
so these telescopes, so there are telescopes which are already existing in United States, Europe, China, Australia, at various places. So what they
So, for
did,
example, they have not taken GMRT into consideration while
because they wanted to observe this at high frequency. That's why I came back to this slide, because they want to get this resolution, which is of the order of like tenths of microsecond arc seconds, and to get that resolution, you want to maximize D as much as possible. So the maximum that we can do by being on Earth is to spread dishes as far as the diameter of Earth. So they chose dishes all across the globe. And then you could also go to frequencies where this is still observable from the astrophysical point of view, but it is not at 1.4 gigahertz or something, which is where GMRT operates. So GMRT observes at lower frequency, and that's had its own speciality. There are certain phenomena uh, that can be seen only at lower frequencies. For example, when we go back to these kind of things, they become much more prominent at lower frequencies, right? So GMRT plays a very important role in understanding these objects. But when we want to look at these very fine detail or very close to the event horizon or black hole, then it can be done at higher frequency. And so they also chose frequency which is like not 1.4 gigahertz, but it's in the range of 200 to 400 gigahertz. So they chose those telescopes which were operating at that frequency to make this theta, the resolution or the sharpness, as small as possible. So that was the
criteria.
optimization aspect of it. That's why GMRT could not play a role in that aspect.
Yeah.
Nice talk, Niraj. Wonderful talk. I could only come halfway in between. I was in a meeting.
Oh,
So
okay.
and
And
it's so good to have it in mobile. That moment I came out, I just switched on the.
Yes.
Yeah.
then yeah, so, yeah. The one more thing actually we thought of discussing today is that see, lot of young peoples are people, they would like, whenever you go there, means whenever there is a talk in astronomy, they end up speaking about black holes. And there are certain students in undergraduate and postgraduate also who forms a part of the audience. So what are the problems which exist in this particular field of research which they can look forward to think about or to know about, to have their future involvement in those
Yeah.
areas? Yeah.
So I think so astronomy especially, and it now actually applies to theory also. The research as a whole is a technology-driven field. Just to give you a specific example of this project, right? Immediate absorption line survey, which we are running, and it's being run on a telescope in South Africa. It produces 1 terabyte of data in 1 hour, and we have got a total observing time of close to 1700 hours of this, right? So we actually have to the raw data itself is corresponding to 1.7 petabytes, right? And this is a huge volume of data actually. I'm sure everyone can appreciate this. So this data we have to now bring in here, set up a complex infrastructure software system which can actually put this data on disk and process it and make these images, right? Now the process on a high performance compute cluster of a very specialized one, just to make all the images from this is going to take us 3 to 4 years. And we are not running it on an archaic system. We are running it on a system which is like as good as it can be in current circumstances, right? So software engineers or engineers, I think, and astrophysicists, and like people who are coming from like pure physics background as well, right? So for everyone, there is an opportunity here to play a key role in pushing the frontiers of science. Like engineers, for example, have to do cutting edge technology to make these telescopes, and then software engineers have to do research at the level of algorithms, at the level of writing complex software to make to produce these kind of images in a reasonable amount of time. And then when those comes out, then we have to have people who can actually uh, understand or interpret these images from their knowledge of basic physics, right? Because astrophysics is essentially an applied field. So there is, and of course, people who can actually have an understanding of more than one domain, like for example, like physicists who can be very good at programming, or the engineers who understand physics, and vice versa, and things like that. Right? The more domains you can cover, then more complex experiments you can carry out. But even in isolation, there is actually I would like to say that, like for students, whether it be of engineering, whether they're coming from like software, data science, or from pure physics, I mean even chemistry background, they all can just within their domain continue and do things without switching their field, right? For example, a software engineer or an engineer would think that, oh, I want to do astronomy, then I should go and actually switch my field and learn something else. No, of course, we have to learn more and more as we go forward in our career, and we have to learn anything that is required to solve the problem of our interest. But it is not really essential to switch. We can just continue in what we are doing, and we can be at an observatory, and we can participate in these experiments. And then again, it is not just about people who are currently getting close to make choice of their career, like at a postgraduate level, even for undergraduates, and if there are any school students also, because these square kilometer array telescope, for example, is going to be around for next 30, 40, 50 years, right? And there is not a single telescope that has been built which actually does only what it has been designed for. Why that happens? Because making these telescopes take 10, 15, 20 years of time, because that's how complex they are, right? It takes that amount of time. So you start with a certain plan, certain goal, certain idea, and you engineer it and you make it. But in those 10, 15, 20 years, the science or the ideas have already advanced, and people start doing things they didn't even think of that they would be doing with that telescope. So even those who are school students in high school now, like they can actually look forward to all these telescopes, being SK, LIGO, ELTA, Topical, and even JWST, which has gone. These are going to be around for next 10, 15, 20, even much longer. Actually, they just need to aim high and stay interested and do well in what they are doing to become part of it.
Yeah. So now, before we are you done with your talk, or you have something?
Yeah, no, I'm done with what I had decided to discuss. But if there are some questions, we can wander around.
Yeah. Now that's what I asked, because now we will open up to the participants for questions, and anybody can unmute and ask whatever they would like to know, or you can put it in the chat also, so that I can see and read it out. In chat up till now, I didn't see anything. Anybody who would like to unmute and ask questions?
Can I ask?
Yeah.
Arvind here.
Yeah.
I'm sorry, I'm going back to the same question again. What is the accuracy in timing this when you say that from all the station when the data is collected, to what accuracy the time is recorded?
Nanoseconds are better actually. That's what
Oh,
they
wow.
aim at. Yeah.
So it's a very highly accurate time.
Yes.
Okay. And the other question that was in my mind also, because these days a lot of people are talking about citizen science and things like that. So are you likely to open up this data for citizens to participate, or is this there is something where citizens or say college or college going student can participate?
Yes. So through this Meerkat survey, we are going to detect several million about 20,000 galaxies in neutral hydrogen and several million galaxies in radio continuum. To characterize them, actually, we are planning to open it up for citizen science so that our friends at different educational background can actually participate directly in the science that can be done with this. And of course, there are a lot of things which can only be done through this way. They cannot be done any other way.
And what kind of minimum qualification they would like, or otherwise just an interest in the subject?
I am thinking of like there will be different segments which would appeal to starting from high school.
I think it's a very good news. I will also pass it on to in our group that there's a possibility of such thing is coming up, and people should consider participating in such kind of activity.
And I can discuss with all of you also before we sort of go public, because there will be many aspects that you will be aware of that we should take into account so that it becomes an enjoyable experience for everyone coming in. Because if it's not enjoyable, it is not. It does not continue and does not lead to, right. So I think we can do it together.
Jayant, maybe I'm just now addressing Jayant. Maybe we can have one separate meeting with him at the planetarians, and then he can inform us, and then we can pass it on. It will be a wonderful thing to do. Thank you so much. Thank you so much.
Something new, people can participate.
Right.
Yes.
And I would also request our other participants who are students that such a wonderful opportunity is there. I think we should make use of it.
And there is one more thing which I have been thinking, but I can talk about it now itself to you, both of you, is that so through this Meerkat survey, we have, it's an international collaboration, so we have 40 researchers across the world. And at the same time, we are addressing with science goals which are very diverse. So I was intending to start a certain interaction with broader community where people that are participating in the project then come and interact with broader community, and it's something like this, but it could be at times maybe more focused, or it can continue like a series kind of a thing. So if you think that I was planning to do it at my level, but if you think that it is something we can do together, that would also be because then we will also get a very good idea of like we can introduce or build towards the citizen science thing in that way as well.
Yeah, we can always.
Sure, it's a good idea. After the ASI, we will reach you. Then we will reach you after the ASI, because right now I'm also a bit tied up because of new projectors coming up, and right now planetarium is not working. But now we are just opening up. So after the ASI, I will certainly reach you with Jayant and other people. We will reach you.
Yes, and we can then discuss what are the actually requirements of the community as well, right? Because often what happens that when we intend to do something, we do it and say that take it, right? This is what it is, rather than going to community in advance and say that, hey, can you tell us like this kind of thing is what you want or not, right? Or should it be slightly different? So maybe that.
Sure.
So because we planning to do this open up in, let's say, 6 to 8 months from now. So
Okay.
this is just, so we are now designing the portal and everything. So now is probably the right time for us to take that input from you and also the broader community through as well. You understand?
I think it's a very good idea.
Maybe we can make a query form, something like we can pass it over to all the or like-minded organization who would like to,
Yes.
who may be roped in, like
Yes.
planetarias and science centers, and
Right.
that way we can make a
Yes.
good
And if needed, we can talk in person also, Arvind. And of course, Calicut, I would love to go, but it's not as easy as going to Bombay.
Yes.
So that's why I'm saying this. But
Yeah.
who knows? We may be in Calicut and Arvind will join from Zoom. But
yes.
but we
Arvind
could,
is always welcome to Calicut.
Thank you. Thank you so much.
We have one question here. Amar Pal Singh. Would you like to brief about some of the internship in IUCA, please? I think it is out of context. If you want to say
no, absolutely it is. So internship. So IUCA itself has its different types of programs, like especially most of them run during summer, like visiting students program and summer school. But for just last 2 years, because of COVID, I think nothing is running in person. So yeah, that's the COVID has stopped many of these visiting activities. But we hope that it will start. We have just started discussion within the institute that can we start this year. A decision is yet to be taken. But if the things stay normal, then hopefully this summer we will have students coming over from different parts of the country and interacting with us.
Sir, I have a small question.
Yes.
Mr. Niraj is a wonderful eye-opening to us. How is that from the SKA, 1 petabytes data, you are able to pull it to your place of working? Or how is it? Is it centrally located, and as and when it is desired, you are pulling it and doing the analysis?
So in this case, what we are doing is that our observations, so 1 petabyte is not is spread over a period of 3 years. So every month or two, let us say we accumulate few hundred terabytes. So what we do is that we can ship them over tapes. And now there are tapes which can carry data like 10 terabytes at a time. One tape can contain tape data of like 5 to 10 terabytes easily. And that turns out to be the cheapest way to ship data. And then when it comes to IUCA, right, we have we put it on very fast disks, and we have an archive which is like already 3 petabytes in size. And we have designed our data processing infrastructure such that our team, which is distributed across globe, can actually log in through a very user-friendly portal and can process this data, look at the images. So we don't have to distribute it further.
ISRO have established it in Bangalore as part of the Science Data Center. Mm-hmm. It's a very huge center. Instead of, to avoid the redundancy of generally storing the tapes and retrieving them as and when it is required. Is it not a solution, or some kind of a dialogue is required with the top management?
No, actually we have to go for it. So our total data volume requirement for the survey is 8 petabytes, right? And 8 petabytes of, if you want to have it all on very fast disks, right? It turns out to be a very, very expensive solution. So, and this is done. This is the way it is done at all data centers.
Okay, sir. Thank you. That is the management issue. Okay. Yeah. Thank you very much.
So you go for multi-layer or multi-temperature archive. That's what it is called. Hot, warm, and cold, basically.
Yeah. Any other question? Okay, so if there are no more questions, I would like to thank the speaker for having agreed to come to our Astrod and spend some time with us. It was a very useful and interesting talk. So, thank you very much.
Well, thank you. It was a pleasure for me too. Hopefully we'll meet again soon sometime.
Yes.
Thank you.
Thank you.
Bye everyone.
Thank you. Bye-bye.